And then we talk about memory model, okay? And for matrix multiplication, we start with basic matrix multiplication, and then we say, hey, you know what, the memory bandwidth is a big problem for these kind of basic algorithms, right? So if we impose a little bit of discipline in terms of memory access and coordinate the memory usage among threads, and they can collaborate and load these data into the shared memory, and then we can save a lot of memory bandwidth, and therefore have the data to be loaded into shared memory at a comparable rate as the compute, right? And also, I spent a little bit of time on Thursday to talk about DRAM, but the takeaway point for that, as far as programmers are concerned, is that if you're not careful with coalescing your memory accesses, the main point is to make sure that every byte you bring in from the memory will be utilized, right? So that you don't waste any memory bandwidth, and that gets you to the beginning point. And then you use the shared memory to satisfy a large number of accesses to that data. You magnify the bandwidth that way, and then you can keep up with the compute. Okay, so that was the takeaway of the matrix multiplication. Matrix multiplication is what we call the staple of computation in science, engineering, and financing. Okay, so that's why we always teach matrix multiplication first. But then, the next level is going to be convolution, what we call the stencil computation. It's a very close relative to matrix multiplication. And so we're going to go over convolution, and then I'm going to introduce constant memory and constant caching. And constant memory is going to be very, very important when all the threads will be accessing a data structure, the same element of the data structure. Remember that M matrix in matrix multiplication? All the threads, neighboring threads, are going to be accessing the same element, right? Unfortunately, when you bring in the entire burst for that access, by the time you get to the second element, there are a lot of activities going on, so the data may not be in the cache, in cache and so on anymore. So you end up accessing the data again unless you use shared memory. But today I'm going to talk about constant memory, and constant memory is also going to be a very, very effective way to handle something like an M matrix. Okay, so so we're going to talk about that in the in this lecture. So the objective is for you to learn convolution. Is a very important parallel computation pattern. All of you who took ECE 210, I think it's 210, and you know Fourier transform, and you should know convolution from the analog point of view. So we're going to be talking about the digital version of convolution, and then the convolution is very, very frequently used in signal processing, image processing, and video processing. So is foundational to solving differential equations and integer equations in engineering applications. So for many of you, it is also the critical component for neural networks. So that's why this is the second topic that we're going to be introducing. And this semester, we're going to make a little bit adjustment to our lecture sequence. So right after convolution, we're going to begin to talk about neural networks and get you ready for the final project. So we're going to be pushing some of the sparse matrix and the scan and prefix sum material a little bit later in the semester, so that we can get you ready for the project earlier. And a lot of the students from previous 2 semesters told us that they wish they had a little bit more time doing a little research on their projects so that it will be more meaningful. So we're, believe it or not, we actually listen to our students, okay? So we made that adjustment so that hopefully it will be even more fruitful for this class. And so we're going to talk about a very, very important technique, that is how we can take advantage of cache memories. We talk about shared memories, and some of you actually ask, how is that related to cache memory? So we're going to answer some of that question today. Okay. So you know what? This is kind of like peeling some of these the onion. You know, you're getting deeper and deeper into these things, and you become more and more confident when you control the hardware usage in your code, when you code. Okay. So let's start with convolution. Convolution is a very popular array operation that is used in various forms of signal processing, digital recording, image processing, video processing, computer vision, and machine learning. Okay, so you know it's probably, in my mind, it's the number 2 computation when people talk about computational methods. And convolutions often perform as a filter. So you have a convolution filter, and that convolution filter needs to be applied to a chunk of data, and that chunk of data could be one-dimensional, so it could be signals, just voice signals or music, right? And 2-dimensional, which will be images, photos, and so on, or 3-dimensional, that will be videos, and so on. So these signals and pixels are going to be transformed in the convolution into some kind of more desirable form. Okay, and exactly how the transformation work out and what kind of purpose that convolution will serve depends on the exact value of the filter. So you can design your filter for the convolution to do various things. Intuitively, you can design the filter to smooth the signal values so that you can see the bigger picture. So this is probably the most, I would say, intuitive way of using convolution. So the way to think about it is that for every pixel in your picture, you're going to be multiplying a small array of mask values or filter values to the neighboring, to the neighboring pixels, and then you do the sum. You take the sum of it and make that into the new pixel value. So a very easy way to think about it is that if I give the same weight value for all the neighboring pixels, then essentially I'm doing an average of the pixel value, of the neighboring pixel value into the new pixel value. So by doing this average, I'm going to be blurring the image, right? We talk about that blurring at the beginning. So this will be a very intuitive way of doing convolution. The others are actually a little bit less obvious, but most of the signal processing people, are very familiar with this. This is a Gaussian filter, which can be used to shorten boundaries. You can actually use the appropriate design of your filter values to make sure that your edges in the picture are sharpened. So that's a little bit less intuitive, but it's actually a very, very frequently used technique in image processing. So if you look at the neural net, the convolution layer belong in the first category. Okay. Basically, we blur these input image and signals, and then we downsample so that we can do what we call the dimension reduction. Okay. And so that's a very intuitive application of the convolution. As a computation, convolution is quite simple. Okay. It's actually fairly simple, almost as simple as matrix multiplication. So we have an array. It's an array operation where each output element is the transformation of a collection of input elements around the original location of the element. And then you do the inner product, essentially the inner product of your weight value with that neighboring, with the neighboring elements, and use the inner product as the output. So that's why convolution is a close relative to matrix multiplication. Inner product is a very, very important mathematical operation for computers for exactly this reason. And so the weights used in the weighted sum calculation or the inner product calculation are defined as, we call them input masks, okay? Or commonly we would also call it convolution kernel. So signal processing people will most likely call the data structure convolution kernel. Unfortunately for this class, convolution kernel will sound like the kernel functions that we launch on the GPU. So it gets confusing. So that's why after we taught this course the first time, we decided to use convolution masks or convolution filters, okay, rather than convolution kernel, just to avoid that confusion, okay? So most likely you're going to hear me saying the masks or the filters. And in fact, in neural net, you know what, most people will call these convolution, the weights that we apply to in the convolution layer, the filters as well. Okay, so that's okay, the filter weights. That's exactly consistent with what we're doing here. The same convolution mask or filter is typically used for all the elements of the array. That is, when we apply a convolution filter to an image, all the pixels are going to be processed by the same filter function. Okay, so that that's a typical way that we apply the convolution computation. So let's start with one dimension. Okay, one dimension. This is very, very intuitive, and it's usually used for audio processing. And when we do speech processing and natural language processing with speech, this is an important step that we often take to be able to reduce the dimensionality of our signals. Okay? Every sample value represents a degree of freedom. So when we try to do speech recognition and processing natural language in speech form, we have a huge possible combination space from all these sample values. So we need to somehow figure out a way to reduce the number of samples to be able to process them in a feasible way. And convolution is definitely an important technique for us to reduce the number of degree of freedom and being able to have feasible algorithms to process these signals. So we will define a mask width. The mask width is essentially the number of neighboring elements, including the element itself. The number of elements, including the element itself, involved in the generation of an output value, right? So if width is 5 in this example, in order to generate P2, which is the 0, 1, 2, position 2 in the output, it's going to take 5 elements. That's why the width is 5. And the middle element is going to be N2. It's the same position in the input, right? So the same position input along with 2 elements to the left and 2 elements to the right, that gives you the width of 5. And sometimes we say this radius 2. Okay, the radius is 2 and the width is 5. Okay? And so when we generate that value, we're going to take the 5 elements from the input, and we're taking the 5 elements in our mask. We do an inner product, okay, the inner product. And that inner product gives us the pairwise the multiplication, and we'll accumulate that value into the final value, so which is which is value 15. Let me see, 3, 8. Oh, so these are the partial products. And then we add them all up as the inner products, and then we get 57. Okay? So this is one dimension. Well, we can move on to the next value. So P3 is the same, it's the same filter, but then it's the next 5 elements with N3 in the middle. Right? So we will do the same inner product and with the next 5 elements, and we produce the value of P3. There's something very, very important to remember. Okay? The access pattern to the mask. Okay? If you look at the generation of P2 and P3, the usage of the mask is exactly the same. Right? We're going to be accessing, for the first step in generating P2, we're going to be multiplying M0 with N0. And the first step of generating P3 is to multiply M0, also M0, but with N1. So even though the N elements used in the process in the generation of P elements are different, but the access pattern into M is exactly the same. Okay? So this is the reason why the M matrix here is a little bit similar to the M matrix that we use in matrix multiplication. Okay? And this is going to be important when we talk about constant memory. Okay? So when we use convolution, there's always a little bit of a problem with what we call the ghost cells, or the sometimes we use halo cells and ghost cells in almost interchangeably, but let's stay with ghost cells for now. The halo cells will be used a little bit later when we talk about blocks, how we partition between the blocks, and the halo cells will be actually across the blocks. So when we calculate an output element that are near the edge, okay, near the boundary here, let's say P1 or P0, there's a good reason why I started with P2 and P3. Okay, P2 and P3 are good because all their 5 elements that they need in the calculation are all within the valid boundary of the original data. But when we generate P1, we have a little bit of a problem, because P1 will require processing 5 elements around N1, right? But this is N-1 right here to the left. It does not exist. So this is what we call the ghost values. These values are not in the original input. So we need to have some kind of policy to essentially take care of these missing values. And the very common technique is to define these missing values as 0. That is, if they don't exist, for inner product, make sure that they don't affect your outcome. So the very common policy is to assume that they're 0. But there are many other techniques that policies that also make sense. For example, you can replicate your boundary value P0. You can take N0 and then just replicate it here. And that's also a reasonable policy, because you just say, I don't know what that value is, but I do know the boundary one, right? So I just assume that it's the same. Okay, just it's also a reasonable assumption. So it depends on what you're trying to do. For image processing, we oftentimes assume that there are zeros, and for solving differential equations, sometimes we replicate the values, right? So these depends on what your physics or what your vision and so on prefer. Okay, so for this class, we're going to, in general, assume that ghost values are zeros, okay, just for convenience, okay? So the 1D convolution is actually fairly easy to write as a kernel. So we can write a basic 1D convolution kernel very, very easily. By this time, you already have written CUDA kernels and so on. So it's actually fairly easy for you to to do this now. Remember, the output is a one-dimensional structure, right? One-dimensional array. So we're going to still assign every thread to generate one output element. So that's why we have this familiar expression I equal to block idx dot x times block dim dot x plus thread idx dot x. This is our go-to expression for assigning every thread to an output element, right? And full coverage. So that's great. And then you have the familiar thing about p-value. Remember, we're doing an inner product, right? So the code should look somewhat like the matrix multiplication code, right? So we start with p-value equal to 0. Where's p-value? Where's this variable stored? In the register, right? So it's going to be in a register in every thread. So there will be, every thread will have a different p-value in its register. And then we have this n start point equal to I minus mask width divided by 2. And this is an integer division, so if you have an odd number, it will be the lower ceiling, right? So 5 divided by 2 is 2.5, but the C convention is just to round off. So it's going to be 2. So this is really giving us the radius of the mask. So we take the center position, which is I, right? The I in the output is also the center position in the input. And then we subtract 2, that brings us to the beginning in the input, right? The beginning of the input that we're going to be using. And then every thread is going to do a J loop, okay? A for loop, okay? For loop that iterate from the leftmost position and with the number of elements in the mask, which is the mask width, right? Mask width, and then do the inner product and accumulate. So every thread is going to be doing exactly the same operation. So we also check, right? We need to check whether or not the input value that we need is actually within the bounds, right? Remember the ghost values, right? So if there's if the n start point plus j, so this is the input, right? So j starts from 0 all the way to, to width, right? So what that means is that we're going to start with the leftmost position, and we're going to add 0 to it in the first iteration, add 1 to it the second iteration, and so on. So in every iteration, the n index that we're using is going to be n starting point plus j, right? So the starting point is the leftmost location, and we just add j value in each iteration to find the real n index. So we test that n index and make sure that it's greater than or equal to 0 or less than width. So that gives us the testing for the n index we're using for accessing the input. Okay, so now it should be very clear. So we use n start point plus j as the n index, right? So this gives us the input value. And m is just a j. Because in every iteration, we're taking either 0, 1, 2, 3. We're starting from the 0th element, and we just increment that j. So j is the index for our mask. So now it should be very clear to you that this policy assumes that the ghost element values are 0. Because if the input element is out of bounds, we're going to do what? Nothing, right? We have an if then else. So if it's inbound, we do this multiplication accumulate. But if it's outbound, we do nothing. Nothing is equivalent to assuming it's 0, because multiplying by 0 will add nothing to your value. So this reflects our policy. And then, so after the for loop, we finish the inner product, and we write the output into the P element. So Pi will eventually get P value. Okay? So one of the things that you should, it should be very clear to you is that this M index only depends on the for loop. It's independent of threads. No matter which thread is going to execute, the first iteration of that thread is going to be accessed M0. The second iteration is going to access M1. And so all the neighboring threads are all going to be accessing M0 in the first iteration, and then they will come and access M1 in the second iteration. So if we access global memory for this, all the threads in the warp are only going to be using one element in the global memory data that we fetch. And then when they go to the second iteration, they're going to go to global memory again and access M1. Okay, so this is not really a coalesced access. It does not make full use of all the bytes that you fetch from the global memory. Okay? So that's 1D convolution. That's a basic 1D convolution. We have 2D convolution here, which is a very straightforward extension of 1D convolution. And this is my poor artist rendition of 2D convolution. And many people who read the textbook told me that I should find a better artist for drawing these pictures. I totally agree. Okay, so any volunteers for fourth edition, I'm glad to take it. When I was in elementary school, when I was in 3rd grade, there was a parent-teacher conference. So the art teacher told my parents, no matter what he does in the future, do not do art as his career. And it kind of hurts a little bit, but looking back, she was absolutely right. Okay, and so telling someone not to pursue something, even though it hurts a little bit, I really, she's still one of my favorite teachers even to this day, even though I kind of failed miserably in the art class. Here is exactly the equivalent. So we take every output element will be generated with a region of input elements with the corresponding input position in the middle, right? So for a 2D convolution, we typically will have a square mask or square filter. And so in this case, we call it a 5 by 5 filter, okay? And we still have the concept of width. So this filter width is still 5. It's just that it's a 5 by 5. The radius is still going to be defined as 2, okay, on each side. So, the definitions are still the same. But then this inner product is going to be a lot bigger than the one dimension. So what we're going to have is that we're going to have 25 elements in our mask. And we're going to be doing pairwise multiplication of all these elements, okay? So we're going to be doing 25 multiplications, and we'll accumulate into the output, right? So these are the 25 pairwise multiplication outcomes, and we'll add them all up into 321. In general, we don't do this, okay? In general, we use fractions for our mask values so that we keep the input and output magnitude roughly the same, right? Otherwise we keep, blowing up the volume or the amplitude or the magnitude of data as we go. So we usually will see floating point fractional values here. This is the reason why, if you look at a lot of the convolutional neural net implementations, the default implementation is always floating point numbers. And then if people want to save power, energy, and so on, they use what we call the fixed point implementation, which is exactly a fractional value, but with, not with floating point capability, dynamic range, and so on. Okay? So this is 2D convolution. 2D convolution also has boundary condition problems, right? And it's actually worse. So you can have the edge, those cells. You can have the top edge, bottom edge, left edge, right edge, and also you have corners. So the corner, like if you generate an output corner element here, almost everything is ghost. Okay, you're going to have 24 ghost elements involved. Okay, and then one real element, right? So the kind of the boundary condition actually becomes worse in 2D, and it becomes really bad in 3D. So we need to worry about this. This is the reason why in convolutional neural net, the input and output sizes are not identical. The standard way in the convolutional neural net is that the input image is usually one radius bigger than the output image, so that when you generate the output image, you're going to be generating essentially this part, so that every element will correspond to all valid input elements in the in the computation. You use all real input values to generate output values, and the first real value that you can generate is actually starting from this location, position, right? So that's why your output is going to only correspond to this part, and there's a reduction of input size to output size when we look at things like Linnet and so on. Okay, convolution layers. Now, so when we have these ghost cells, we do the same thing. We can assume 0, or we can replicate boundaries, we can do whatever we want. So here we just use the 0 as our input. So we do the same thing. We test whether the the horizontal and vertical row and column indices are within the range. If it's outside the range, we don't do anything in our inner product, and that means that we assume it's 0. Okay. So let's go back to this access pattern for M. So I already talked about it. So I used to only talk about it here, but some of the students mentioned to me before that if we can actually kind of mention that M access pattern along the way, it becomes a lot easier to see and a lot more intuitive for everyone. So we decided to do that. So the elements of M are called the mask, or kernel or filter coefficients, or the filter weights, or mask weights. So the calculation of all these P elements need M. So M is small, okay? So in our previous example, M is a 5 by 5 small matrix, 25 elements. Whereas the images can be big. The images for, let's say, high resolution images are oftentimes today 2K by 2K pixels, right? So these are huge things, millions of pixels. But the same 25 will be applied to a large number of pixels, right? So, and also every output element will be accessing M in exactly the same pattern. The 25 elements will be accessing exactly the same order. And so this is going to be important. So the M elements are accessed in the same order when calculating all the P elements. And this is a very, very good access pattern for what we call the constant memory. And another important part is that the mask is not used during, is not changed in the convolution. So, you know what, we may be processing multiple images. But so the images may change. On the other hand, the masks will not change. The mask will be used in processing different images as well. So the fact that we can launch a kernel and we can depend on the fact that the M array is not going to change, okay? It's not going to change, and it's going to be accessed by all these different threads in exactly the same order, give us a perfect candidate for using constant memory. The origin of constant memory is that you want to be able to, in graphics, you want to essentially use the constant memory for exactly like this, the filters. And these values are not going to be changed, and they're going to be applied to all these pixels, right, in the same way. And so graphics processor always had constant memory. And you can also think about constant memory as the coefficients of the equations that you solve in the in science and engineering applications. When you solve a differential equation, linear equation, and so on, the coefficients of these equations don't change. The solutions change, right? The coefficients don't. So those coefficients or polynomial coefficients you can use constant memory for acceleration. Okay. So this goes back to the CUDA memory picture that I showed earlier. Remember we talked about read-write per thread registers, right? So by now everyone should be extremely familiar with the registers. Yes, I see a question.
So, we did change the
Yeah. Right. Yeah. 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 For that respect, the M matrix so far is exactly the same as the mask matrix here. Yeah, so far. But then I'll get to a very important difference. Very soon. Very good question. Thank you. So the rewrite per block shear memory, you also use that for matrix multiplication, right? So every thread block can have this shear memory, which is up to 48K bytes per block, and we use that to store tiles of M and N matrices. So these are per block accesses, and then they can be accessed, these data can be accessed in about 5 cycles. And when we use shared memory, we need to explicitly load the global memory data into the shared memory. And if we write anything into shared memory and want to reflect that into the global memory, we need to move the data back into the global memory. So in your code, you will declare the shared memory variables and arrays, and then you will see statements moving the data back and forth, right? So that's shared memory usage. And then we have the read-write per grid global memory. Some of you asked, I think one of the questions on the Piazza was that, is this really per application or per grid global memory? The answer is, per grid means the access scope. That is, all the threads in the same grid will see the same variable. But when you write into the global memory, the data will persist as long as your application is running. So you can launch another kernel, and that other kernel can see all the values produced by the previous kernel. Okay, so that's why the lifetime of the global memory variable is entire application. Okay, so now we're adding the constant memory. So the constant memory is actually conceptually located in the same level of the memory as the global memory. Okay, so the host can copy data into the constant memory. Okay, can copy, and I'll show you the API function. So, it's actually done in the same way, very similar way to global memory. However, the constant memory is automatically cached. So there is a dedicated caching mechanism in hardware that will be caching the frequently used components. Remember, this M is very, very small compared to the input, right? Which is different from that M matrix in the matrix multiplication. The matrix multiplication, M and N matrices are comparable. But in this case, the mask is a lot smaller than the input. Okay? So that means that if you have a small hardware that automatically captures these values and then put them near the compute unit, you don't need to have much hardware. In that case, 25 elements will be good enough, right? So you can actually have a very easy mechanism to to store that as cache value. So the constant memory, when it's cached, is automatic. That means that as a programmer, your code looks like you're just accessing the data from the constant memory, but you can probably expect 99.99% of the time the access to the constant memory will actually be served out of your little cache near the compute units. Okay, so that's why with caching, it's about 5 cycles. With caching, or even fewer. Okay, so the constant memory actually has limited capacity. So you cannot use more than 64K of constant memory for your application. Okay, so the host can load different 64K's worth of data into constant memory. But once you load that constant memory, you can load up to 64K, and you cannot change it in the kernel. The kernel cannot make any changes to the constant. Okay, and the kernel can, the host can load another up to 64K's worth into constant memory before launching another kernel. That's fine. But then that other kernel cannot make any changes to constant memory contents either. Okay, so the constant memory is really relative to the kernel, and the host can do whatever it wants to set up the constant memory for the kernel. Okay, right? Okay, good. So let's take a look at the memory hierarchy. So if you had to go to global memory to access data all the time, the execution speed of GPU is limited by memory bandwidth, right? I already have said that so many times. If I say that any more times, you guys should start to protest, right? Professor Hu, we know this by now, okay? So, but trust me, I'm saying this one more time for your own good, right? So we saw the use of shared memory in tile matrix multiplication, and so today we're going to actually talk about this caching thing. So a cache is an array of cache lines, and these things are hardware, the hardware mechanisms, and just like shared memory, these are hardware, they're hardware memory blocks inside these processor cores. And the cache line can usually hold data from several consecutive memory addresses. So this is called the cache line or cache block. Constant memory is just a form of cache, but the contents of the cache cannot be changed by the threads. Okay, the threads that access this data can only read, they cannot write. Whereas the normal data cache, you can write or read into that cache, right, into the normal data cache. So when the data is requested from the global memory, that is the first time your kernel, one of the threads in your thread block, or one of the warps in your thread block try to access a piece of data in the constant memory, the hardware will automatically, transparently, and so on, take an entire memory burst, okay, and put that into the constant memory, cache, putting into the cache, and use a hardware tag mechanism to remember that these bytes correspond to the memory address so-and-so, that's where the memory burst came from. And I have all the bytes in that burst, okay? So in the future, if these threads access any of those bytes, you can get it from the hardware mechanism rather than going back to the global memory, okay? So this is really intended to give us some locality, take care of our locality so that next time when the threads access any of those bytes, they will be able to get, get it from the cache. So the data in the cache is really a copy of the original data. This is very, very important to remember. Anything you put into the cache, you always have a home copy in the global memory. Whereas in shared memory, you could allocate a shared memory location and just write into it. There's no copy in the global memory until you explicitly move it into a global memory variable. But in cache, there's always a very strict correspondence between the cache version and the global memory data. So additional hardware is used to remember where each cached data byte corresponds to in the global memory. That correspondence is always maintained in the cache. We don't really teach the texture memory. And texture memory is also cached. So there is another caching mechanism for textures. And that is, everything I said about constant memory also applies to the texture cache. The texture is a totally different animal, so we're not going to really go into that. But some of the students actually use texture cache for their project. Okay, so I just want to mention, but with all the things that we learned, you should be able to learn about texture cache very easily. And we will make some resources available for those of you who want to use texture cache in your projects. So there's some definitions. There's a concept of spatial locality and the concept of temporal locality. Spatial locality says when a program accesses a data element in the memory space, it's very likely it's going to also access locations nearby, okay, the nearby locations. If I access a particular piece of data, chances are I will probably access the data around it. Okay, so that's spatial locality. Temporal locality means that if I access a piece of data in the global memory, I will likely revisit, okay, and reuse that data in the near future. Okay, so that's the temporal locality. Cache captures both. Remember when I talk about constant memory, when the DRAM delivers a burst, okay, of the data, that cache will capture that burst. So if you access a particular piece of data in that burst, the cache will capture the rest. So because the assumption is the program will likely access the nearby locations. And also the cache will try to keep that data for as long as possible because it assumes that the program will come back and ask for the same piece of data in the near future as well, right? So that's spatial and temporal locality. Both spatial locality and temporal locality are important for the performance of caches. The fact that a cache line spans multiple words uses spatial locality. And the fact that you have multiple entries and you try to keep the data for as long as possible in the cache means that when the program revisits the data, it's likely you're going to see that in the cache. Okay? Now, so this is really the summary of difference between shared memory and constant cache, as far as you're concerned. Scratch memory, which is a shared memory in CUDA, but in general called the scratch pad category, is another type of temporary storage used to relieve memory contention, and you need to explicitly manage the use of shared memory. You declare variables in the shared memory, you move data in between the global memory and shared memory. In fact, some of you also asked that question. When we have the tile matrix multiplication and we're loading from M and N matrices into the shared memory version, the tiles, inside the hardware, really what happens is that you're actually loading the global memory into your registers. Okay, you don't see that register because compiler managed that register, and then you store the register value into shared memory. All this is take instructions. There are actually extra instructions for you to do all these things. Whereas, if you use caching, that means that you only mention the variable in your code, okay, and then the variable will be loaded into register, right? But in the process, the hardware actually transparently take that value and its surrounding value and put that into the cache without additional instructions. You don't need to do anything extra. The hardware does all this for you. Okay, so you only see the load, and in fact, if you use scratchpad memory, remember in the inner product loop, we actually use the shared memory tile variables, right? The tile variables in our inner product. But if we use caching, we will continue to use the global memory variable. It's just that the hardware will automatically detect that this variable now is in the cache. So it will use the cache value instead, and it doesn't go to the global memory. But as far as the programmer is concerned, you're still trying to access the global memory or constant memory location. Does that make sense? Okay. So for someone coming from 408, you really need to understand this. And if you interview, when people ask you these questions, if you cannot answer these questions, all these recruiters know me. Okay, so they're going to come back and ask me, what did you do with that class? Okay, how come you didn't teach them properly? So, I don't want to get those kind of feedback. Okay, so everyone make sure that it's crystal clear, what the difference between shared memory and constant cache, constant memory is, right? Okay. So when we use constant cache in GPUs, there are some API functions that that are available to the programmers. So if in general, if we have a CPU cache, the CPU cache will allow you to write into that cache because the CPU data in general, it's a rewrite data. So when we talk about data cache in CPUs, we need to have a mechanism for the CPU data cache to be able to handle writes. And what does that mean? If you're taking 411 and you're taking probably 433 in CS, we teach things like write through cache, write back cache, okay? And these are the write handling policies. Right? So those are the additional things that the hardware needs to be able to do because of the handling of writes into the data. But for constant cache, because constant cache will not be changed by the threads in the kernel, so we don't need to deal with any of these write policies. Okay? So that's why the cache design is quite a bit simpler. So data declared in the constant memory will not be modified during kernel execution. So the constant cache can be accessed with higher throughput than L1 cache because the design is much, much simpler, and they can play a lot more tricks in terms of allowing many, many threads to access the same data. So essentially, because of there's no need to worry about any change into the contents. You can buffer things, you can do all kinds of replications, and that's why the constant cache can be accessed by many, many threads at even higher throughput, okay, than typical shared memory or even L1 cache in the designs. So how do we actually use constant cache? The host code will allocate and initialize variables pretty much the same way as any other variables. So constant doesn't mean anything to the host, okay? The host, as far as the host is concerned, is still just preparing data and so on for the GPU. So the host, well, let's say the host would, read in, let's say the mask values, okay? And then it would copy the mask values to the GPU using CUDA main copy to symbol. So this is similar to CUDA main copy, okay? But it's called CUDA main copy to symbol, and its destination, source, and size is number of bytes. So that's the same, okay? So the copy function tells the device that the variable will not be modified by the kernel, and they can be safely cached by the constant cache, okay? So the symbol is actually a historical term for these coefficients and constants in the in graphics programs, okay? So in the host code, we can, this is an example host code. So we have a mask width, so 5 by 5. We just define the mask width to 5, and then we define the the constant sort of the filter or the mask array or matrix. So here we use a industry standard matrix object representation. And so for each matrix, it actually comes with its own, what we call the metadata, okay, the metadata to describe what this matrix is about. So, in addition to all the elements, there's 3 words in front of all the elements, and that's the metadata, okay. The first metadata is width, the width of the matrix, and the second one is the height of the matrix, and the third one is the pitch. And pitch, don't worry about pitch for as far as this course is concerned, because pitch will be always the same as width from our applications. Pitch has to do with what we call the submatrix in the C layout. So oftentimes, we will actually define a submatrix inside a bigger matrix. So you oftentimes will have a submatrix that is, let's say, 5 by 5, but then it can be in the as part of a bigger matrix that is let's say 100 by 100. So the pitch is actually the width of the bigger matrix, and the width is the number of elements in that submatrix. The most frequent use of pitch is when we do what we call the padding of matrices. It turns out that in most of the CPUs, if your matrix is not, the width of the matrix is not a power, the multiples of 16 or 32 words, you will run into what we call the alignment problem when when you access the matrix, the matrix rows. So a lot of times when the matrices are of strange size, let's say 87 by 52 or something, then the tradition is that we actually will pad each row with additional elements to make them into the multiples of 16 or 32. And for a lot of the CPUs, this actually can improve the performance of many libraries. So what they tell you is, you're going to see a padded matrix of, let's say, 80 elements. Okay, that's multiple of 16, isn't it? On the other hand, the real image that you have is only 52 elements in each row. So the width will be 52, and the pitch will be 80 for that. Okay, but here, for the purpose of this class, we're not teaching image processing, and we're not teaching those kind of things. So we're just going to make these images nice sizes and so on. We're not going to do padding, so that's why the pitch is going to be the same as the width. So this is an industry standard way of, representing matrices and tensors and so on, in industry. So, the host is going to assume this kind of object format. So when we allocate a matrix, you will see a matrix, allocate matrix in the host code, and that allocate matrix will do the following. It will allocate space, okay, allocate space for all the elements, and also initialize the metadata, right? So you know, when you need to allocate matrix, you give it a height and a width, and then some kind of initialization mode. So these library functions oftentimes give you different ways that you can, you know, give you choices of how you want to initialize your, you know, your object. And this has to do with different performance requirements and then different degree to which the users want to be able to do their own things instead of having the library to do everything for them. So, you know, inside the allocation, you know, matrix allocation is going to, you know, have this, you know, the type M, and this is really a, you know, a static variable that has all these, you know, structs. It's a struct, and then you will have width. So this is the width metadata, and so for the purpose of this class, the width and pitch are going to be initialized the same into that width, and then the size is going to be the width times height. So that's the total size of the matrix, and then the elements, you know, we're going to initialize to null, and then depending on the initialization mode, we're going to have mode 0, mode 1, and mode 2. And basically for mode 0, we just want to initialize all the elements to 0. Allocate this matrix and initialize everything to 0 for me, so I get a clean matrix, right? And initialize 1 means that, you know, just random, give me a random initialization. This is actually how we generate the test data for you, okay? We you know, do the random initialization. And then, you know what, if it's true, then initialize the metadata, okay? But don't allocate memory. And this is usually done by users who want to manage their own memory allocation. So essentially, they will reuse their matrices and so on by allocating a new matrix and get a null pointer back and then just point that null pointer to whatever it's currently using to avoid some of the repeated usage, you know, the memory allocation overhead if they just repeat to recycle the matrices. They're trying to eliminate some of the memory allocation overhead. So the users, this is a very typical example where the users may actually do a little bit of a pool allocation of his own or her own to avoid the full strength memory allocation overhead. Okay, so these are all very typical library design kind of things. So, you know what, again, you know, we're not teaching library design and so on, but, you know what, for those of, you know, everyone here, you're graduating, you know, you're going to, you know, go to internships and so on, so you should be sensitive to a lot of these design decisions when people provide APIs and so on. So this is a good example of an API function that needs to provide these different options because the users may want to have all these different functionalities, and then the users may want you to do more, want to do less for them. So, you know, you provide them with all these flexibilities. So if the mode is 2, then you return M because it tells you not to allocate memory, right? But if it's not 2, so it's 0 or 1, then you take the size so that you know, it's height times width, so then you do the malloc. You actually go and allocate memory for that matrix. And so these are all the elements. And then you initialize all the elements. So if it's 0, that means that you want to initialize the mode 0, then you just assign 0.0f to the elements. But if it's not 0, that means that they want you to do a random initialization. So you call the random variable generator, rand, and you divide it by the rand max. That gives you a fraction, right? Divide by the max value, so this gives you a fractional floating point random value, right? The random C random variable function is an integer function. It gives you an integer return, okay? And it's actually positive integer. So that's why if you want to have a balanced positive and negative value matrix, then what we do is we have some random way of turning some of the elements into negative values. So this says, you know, whatever integer value that you have, you generate a random number. If it's an even number, then you know what, we're going to just you know, keep it the same. But if it's an odd number, we make the element, the corresponding element, a negative number. So we have a randomized equal number, roughly equal number of positive and negative elements. So this is how we generate that balance matrix for you. Okay, so in the host code, this is important, and in fact, it's going to be even more important when you start to do project. So you're going to declare a variable. So this is how you can declare the constant memory variable for use by the kernel. Okay, and remember, the constant memory has the scope of the entire grid. Okay, so it needs to be, so this constant underscore constant keyword declaration need to be made outside any kernel, because all the kernels should be able to see this constant array. Okay, so you put this declaration outside any of the kernels, and then so you have a m with a constant. This is just a arbitrary naming convention we pick, and you can pick any naming convention you want, but it's mask width by mask width. So the 5 by 5 will give us the 5 and 5 in our declaration. So this is outside the kernel, and then in the host code, you're going to have to allocate the n, p, and initialize all the n elements and copy n to the n device. So we do the allocate matrix for n. Okay, so remember this thing is going to be copied to the constant memory. So you will see CUDA main copy to symbol, and the destination is going to be the source is going to be the m elements, and then the destination is going to be this MC, okay, the MC array, and then the size is going to be the number of elements in that mask. So it's the mask width times the size of. So we're not copying the metadata. We're taking just the elements and copy all the elements into the constant memory variable that will be visible to all the kernels in the GPU. So using this CUDA main copy to symbol. And then when we launch the kernel, we only need to launch the, remember we're also doing the regular CUDA main copy of the n array, right? The n array, but I don't need to teach that anymore, right? It's exactly the same as the matrix multiplication copy. So, but when we call the kernel, we launch the kernel, we only need to provide the pointer to ND. So n is the global memory version of the n, right? And the product, the output P, right? But we don't need to provide any pointer to MC, because MC is a global variable. It's visible to all the kernels. You can just refer to MC in your code. Okay, so you don't need to have that in the as a pointer in your kernel. Okay, so this brings us to the next MP. So you're going to actually do the the convolution lab, and you're going to pay attention to the declaration of the constant array, and then MC, and then you're pretty much doing the same thing for N and P as you did in the matrix multiplication. And then inside the kernel, you're going to be doing a two-dimensional convolution, and I did not give you the code, right, for the two-dimensional convolution. So you know what, you should be able to to do that on your own. And then next time, I'm going to let you go a little bit earlier today, but next time I'm going to be streaming down from Chicago again, okay? And we're going to be talking about tiled convolution. And so essentially what we have is that we put the M matrix in the filter matrix into the constant memory. So that gets transparently cached, so we save the memory bandwidth for that. On the other hand, we still have the N, right? We still have the N. So how are we going to save the bandwidth for N? And that's going to require the use of shared memory. And so this goes back to, to that question. I want to circle back. You can use constant memory when you know for sure that, that your data is fairly small. Okay. So for filters, these are 5 by 5. So even 11 by 11 is not huge. Okay. 11 by 11 is 121 elements. So that's only about 400 bytes per single precision, almost 500 bytes. Small. Okay. As long as it's smaller than 64K, you can definitely use that. But for matrix multiplication M, you can easily have 1,000 by 1,000, 2,000 by 2,000. The size of the M matrix is unbounded, right? For real applications, if you have a matrix multiplication function, you need to be able to take arbitrary input sizes. So you cannot say that the matrix will be definitely within 64K by 64K bound. Okay, so so we still need to be able to handle that N array. So we're going to talk about the tiling of the N array, and the tiling of the N array is going to be a little bit different than the matrix multiplication because remember when we need to process, generate an output tile, we're going to actually need to have more data elements from N on each side, right? So this is why I mentioned something like the halo cells. So for next time, we're going to go into the concepts of halo cells and how we can maintain some of the memory coalescing and so on when we need to handle halo cells when we load data into shared memory for convolution. Okay. So today is Tuesday, and everyone is finishing up the MP4. I think MP5 should be posted by now, right? Okay, yeah. So from this point now, we're going to be at least one ahead, so that for those of you who are traveling and need to do the interviews and so on, you should be able to go ahead, be ahead of the schedule. Okay. We're not going to take any points off if you finish early. Okay. Any additional questions so far? Everything pretty clear? Okay, so I will see you on the stream on Thursday. Okay?